Welcome everyone to this session of the webinar series from the Geoscience Remote Sensing Society's technical committees. This presentation is going to be brought to you by the GRSS Standards for Earth Observations Technical Committee. And I have invited Dr. John Gilchrist to make the presentation. He is the current chair of one of the working groups working on standards development, and he'll be explaining that to you. I just wanted to say by way of introduction that the GSEO Technical Committee sponsors projects that are carried out within the IEEE Standards Association, but has a general scope of looking at where standardization can help advance remote sensing, the applications of remote sensing. So we also work with the ISO and the TC211 and the Open Geospatial Consortium. But today we're going to hear from John on how the standards development process works with one of our longest running committees, P4001, on calibration and characterization of hyperspectral imagers. So, John, please take it away.
Well, thank you very much, Siri Joda. That's a very nice introduction. Let me explain first that I am an applied physicist. I'm not a geo-type person. And my engineer friends say that an applied physicist is almost as good as an engineer. So I hope from that we can have a constructive presentation today. I've been very fortunate in my career because my whole life has been in optical spectroscopy, and particularly in making and measuring rainbows. And so it's a super happy life. And I'm very pleased that I'm participant in the P4001 working group. Originally as secretary, but as of last week as the new chairman. And I've got very big shoes to fill in this case because Chris Darrell is also still on the committee, and he was our first chairman and did a fantastic job. So the pressure is on for me now to at least succeed as well as Chris. We're super pleased that GRSS and IEEE are sponsoring this work program. Simply speaking, there is a real need for consensus in hyperspectral imaging performances. And the reason for this is that there are now fantastic spectral camera designs. There are an unbelievable number of applications across every single area that you might think, from medicine to agriculture to defense to machine vision and so on and so forth. It's, we have a project portfolio from beef to tomatoes to other vegetables to medical applications for burn and wound management and so on and so forth. As a result of that, and also because of the way that these instruments are deployed in such a wide range of modes of operation and methods of data acquisition, along with different types of customers who might be in machine vision or might be in remote sensing or might be medical or whatever, everyone speaks a different language. And that is a real problem, because what one person means by a spectral camera is not necessarily what is meant by another person, or gosh, even what is meant by hyperspectral imaging. We'll come on to the definition of hyperspectral imaging in a little while. But what does that mean? It means something quite uniquely different to every single person. Hyperspectral imagers encompass many modes of operation. So but every single one of them has the primary purpose to do optical spectroscopy in some form. How they acquire and collect the data and how one talks about their performances is in many ways specific to the method of operation. In the P4001 group, we very early on made a consensus that we should concentrate on push broom imagers. And the reason for this was that these are the most popular spectral imaging cameras that are used today. Many thousands are deployed each year in many, many applications. And they've been around for more than 30 years. They can be applied in different ways, but they all encompass all the key things that are required for you, the user, the customer. And that is that they provide information or they provide data, which you can then provide information from. So they all have an objective lens. They all have some dispersive or wavelength selection device. They all have a detector system. So they all have a common set of requirements. Now, the problem comes in that for every camera manufacturer and every application area and every mode of scanning, oops, I beg your pardon, that there is not a consistent and terminology for a particular parameter. It means that each manufacturer has their own term which means something. For example, spectral resolution. What does spectral resolution mean? In one manufacturer, it means an optical resolution based on the Rayleigh criteria. In another manufacturer, it means the spectral sampling interval, in other words, the number of bands that one might have in the data cube, and so on and so forth. At the same time, how one defines things like smile and keystone and radiometric performances are individually done. And there is a real need then for a harmonization in this. A harmonization allows us to have a terminology which identifies a particular parameter having one word and therefore one meaning associated with it. And that's the purpose of our P4001 group, to focus on the technical efforts that are required to provide that consistent terminology, testing, and performance of parameters. As I said earlier, we concentrated on push broom. Of course, we could use tunable filter or other types, spatial, other types of system as well. But push broom being the most popular and encompassing a wide spectral range, it follows our charter precisely. And it means that we have to develop a standard which is applicable to grating-based systems in the first instance as version 1, and a range of focal plane array detectors like silicon or indium gallium arsenide and so on, which define an operational range of a sensor system. Now, all of this can only be achieved by you, the community. And it is the case that the P4001 group is a community of industrial and academic and national standards bodies who have come together in my opinion, one of the most open and thought-provoking groups I've ever been involved in. The fact that manufacturers are opening their ideas to this group is just fantastic. In many cases, one would have thought that they would have been trade secrets and therefore by keeping those things secrets, it would be a commercial edge, a commercial advantage for a manufacturer. It is stunning to me that we have all of the major manufacturers openly discussing what they do. I simply am shocked at that. So, as I said earlier, GRSS is our sponsor, and we are very thankful for this. And they have made already in the last 2.5 years since we started this project a super interesting set of tasks for me, originally as a secretary, and will continue to do so for almost the next 2 years. Our working group is subdivided into smaller groups, and it will come into even more groups soon, because the actual task of preparing a standard is in fact a rather big task. And even though we have more or less 230 people in the working group, we only have a core of about 30 people who are the diehards, who are those people who are at every single meeting. And they are the ones that contribute to our subgroups. And today we've defined those groups as being a terminology group, a characterization group, and a metadata data. I'm not going to say data processing. That's not our job. That's your job as the user. But our job is to find a minimum set of criteria that will be a minimum core metadata set that allows you to do your fantastic science research stuff. Each group is in fact fully interactive with each other. It has to be. For example, characterization, if we talk about coregistration or spatialspectral values, there are terminology, there are words which describe all of this. And we have to have a common language, and that common language has to be written down and agreed upon. All of this then requires us to try and bring a consensus to the party. And I really mean party. It is a super exciting thing. You'll see in a moment. We have to bring consensus. I talked at the very beginning about the idea of what is the definition of hyperspectral imaging. Believe me, the definition took more than 2 years to hammer out. It's unbelievable when you think about it, isn't it? That to actually define the core thing that we are talking about took 2 years, and that took 2 years of proposals, discussions, documentation, reiteration of all of this, coming to a vote, changing that because we didn't like the outcome and it wasn't correct, and we then went back and discussed again and redocumented and revoted. You know, you can see the gray hair. I'm actually only 35, but you know, this is 2 years of gray hair because of the definition of hyperspectral imaging. I'm going to read it out now. You may or may not agree with this definition, okay? So we defined a minimum viable definition for hyperspectral imaging. That is, for the purposes of the P4001 effort, we are addressing systems operating within a spectral range 250 to 2,500 nanometer. And that a hyperspectral imaging system or a data set is defined as one that covers a specified spectral range without gaps and with a maximum spectral sampling interval not exceeding 1/30th of the spectral range. That took 2 years and 30 industry specialists to define. And I'm very happy with this definition because last week I gave a keynote presentation at another conference, and the previous speaker identified something as being hyperspectral of having more than 20 more than one as being a spectral range divided by at least 20 sampling points. So yes, our 2 years of hard work identified a reasonable definition. So one has to think about being, now we have a definition, what are we going to characterize? So we go through exactly the same process. So we make a proposal, we make a discussion, we make a document, we review that document, we discuss, we vote, and so on and so forth. I'm not going to go into all of the gory technical details here, but suffice to say that there are some key characterization things that we have been working on. And that is Spatialspectral. And that's one of the clear tasks of a subgroup. And not only to define the operational parameters, but how to test this in real life situations that the normal person can, if they wish, in their laboratory test. So these characterization methods require very clear definition of what we're going to test, and very clear definition of how to test it, and what sort of parameter would be a value that shows a performance that can be transferred from instrument to instrument, or manufacturer to manufacturer, or laboratory to laboratory, and so forth. And to be able to state this in a way which is sufficiently clear for the normal person to use. So for example, spatial and spectral co-registration. Clearly we can define this mathematically, but it's a misregistration of the spatial and spectral axes. And we've come up with an idea of representing this in terms of sharpness of a camera and effective pixel counts, and then a misregistration value. So, oops, I beg your pardon. So when we talk about the sharpness of a camera, if we look at across the track or along the track, then the value is the blue line here. So the higher the value, the sharper the camera. The lower the value, the less sharp the camera is. That means that the energy that is recorded by the pixel is concentrated or more in that pixel or not more in that pixel. The misregistration is the bottom two graphs, where we have a maximum misregistration value and a average misregistration value. So the lower the value in misregistration, the better the registration quality is. So we got two metrics. Sharpness, the bigger the number, fantastic. It's easy to understand. And misregistration, the smaller the number, the better it is, so the easier it is to understand. And we can apply this in a very simple graph that almost anyone can look at and get an indication of the performance of their camera. So we don't need to describe it by the complex mathematics. On the other side, when we come to think about radiometric models, the recording of photons by the spectral camera, then it becomes yet again another complicated mathematical problem involving wavelength, field of view, effective radiometric parameters, and so on and so forth. And what we measure is a big convolution of lots and lots and lots of stuff. And each of that then forms a measurement which we make, and we have to understand how our measurement system influences that, because what we truly want to have is a radiometric performance in terms of the radiance of the radiance detected by the camera itself. And particularly in remote sensing, that becomes a very important parameter. I'm fortunate, I come from machine vision point of view primarily, And in machine vision, we don't really care about the radiance. We care about the reflectivity. And we can put a white tile down and we can measure the reflectivity. So we're in a very nice, more controlled, dare I say it, environment. And we don't care where the sun is and we don't care what angle the sun is at. We have our tungsten lamps and we're happy people because we have that. So our requirement for characterization is slightly different. But of course, all of this requires a proper radiometric model. And the problem with radiometric models, as I said earlier, is that we cannot measure everything independently. So a range of parameters become a convoluted parameter, a parameter which encompasses many, many artifacts. And that's what we've been trying to do. And we've been trying to understand and present things like relative radiometric responsivities and quantum efficiencies, and so on and so forth. Now, with any standard development, we don't want to just use what we think is our best way of doing it, because there are many people out there who are doing rather similar things. In the our sponsor is also sponsoring the P4005 group for soil spectroscopy. And we're also working very close with the European Machine Vision Association, the Enva people. And particularly EMVA 1288 has many parameters and many definitions and a very clear radiometric model for their sensors. So by working with them, we are able to piggyback on top of what is already an established industry standard for machine vision cameras. And that's really super good news. And similarly, if we talk about stray light, which is the limiting factor of many detection systems, it gives you the limiting detection. We can use things like the ISO 935-8 standard for viewing glare measurements for image forming instruments. And that is a standard which is well established for imaging systems. And of course, a spectral camera is simply a, dare I say simply, a special type of imaging camera. So we can use this to form methodologies for measuring the stray light performance, both from an imaging point of view and a spectroscopy point of view. Ultimately, the key output is the data. And that's what every customer wants. In fact, how you get that data is important in some ways, but I had a boss many years ago that said, it doesn't matter, John, what is inside the instrument, so long as the data is reliable and proper. And his view was, he was Irish, and he said that it doesn't matter if there's a little leprechaun inside the camera. So long as that leprechaun gives you the right numbers out, then everyone's going to be happy. And that's really true for many people. Now, in the data structures group, this is interacting with both terminology and characterization. It's not, all of these things are not independent. We have concentrated on two areas, remote sensing and machine vision. And I'm really happy to say that we have specialists in both areas. And those specialists are Barbara Eckstein, who developed the Snip standard, and Jan Makowski from LuxFlux in Germany. The key here is for this group to provide the generic headers and data file structures that are inherent in hyperspectral imaging, and to be able to document those parameters so that we have a minimum viable header structure. Even if one takes conventional structures like Enva, it depends whether the data set's recorded in BIP or BIL or other formats and so on. And on a manufacturer's side, it depends very much upon what additional data one might add into, additional metadata one might add in. So a user has sometimes difficulty to really interpret and use this. I don't want to look really more in detail at Snip, except to say it's an extremely comprehensive set of metadata that is used for not just preparing the initial raw data files, but providing a workflow for how to correct that data and how to provide information from the measured data. I said also we're working very closely with Enva 1288, and we started with the version 3.1 process, and now just recently, 2 weeks ago, Professor Yaron, he published version 4, and I would encourage people to go and look at that as well. At the same time, version 4 is beginning now to look at snapshot multispectral or hyperspectral cameras as well. Those are cameras based on filter mosaics and other things. And we will work with Enva 1288 in this mode as well. Oops, I'm sorry, I'm having some computer problem today. Obviously, I'm very far too excited in giving this presentation, and the button is hairline trigger today. So sorry for this, folks. We're also working with ISO on the and just starting to participate in the 19159 program. And I mentioned earlier that soil spectroscopy P4005 has many things related to what we're doing as well in terms of optical spectroscopy and radiometric requirements. So there is maybe something that P4005 could take from our work in hyperspectral imaging. Just to finish off, it's not just work. I said right at the very beginning, I have had a fantastic, wonderful, enjoyable working life. And the reason for that is that we meet and interact with wonderful people. And we're able to present our views and listen to the views of them. And in this process, one can feel a contribution to something that is genuinely useful for the scientific and industrial communities. And out of this will come version 1 hyperspectral standard, and version 2s and 3s will come in the coming years as we progress, and we'll add additional modalities and additional types of spectral camera and so forth, all in a harmonious and a consensus fashion. It's important that you, the community, share in this process and share in our excitement and joy and fun of doing this. And I really mean joy and fun. It is the first case that I have experienced where the manufacturers and the users and the national standards bodies are all working closely together and enjoying what they're doing. That's not to say that there are not disagreements, of course. But with proper rational logic argument, then one can reach the consensus. And I would like to very, very much invite all of you to participate. And by that participation, we will get better and wider inputs, and we will get the opportunity to develop a better standard and one which is more comprehensive and clear for the wider range of applications. And with that in mind, I welcome new members to the group, and I want to thank you very, very much for your kind attention and welcome questions.
John, thank you.